Welcome everyone to Economics 1723 Capital Markets. This is the module, the online module for the 7th lecture, and I'm going to record this in two parts. This is the first part on the beta representation theorem. We'll do a second part separately for the capital asset pricing model. Okay, so what is the beta representation theorem? This is the following. We're going to think about a situation where we have a risk-free asset with return RF. We have a complete portfolio C, which is mean variance efficient, and we have an arbitrary risky asset, which we write I. Then the result, which I'm going to show you, is that the average excess return on asset I over the risk-free rate must be the beta of asset I with the complete portfolio times the average excess return on the complete portfolio over the risk-free rate. And what is beta? Beta is a regression coefficient of asset return I onto the complete portfolio return. In other words, it is the covariance of the two returns divided by the variance of the complete return. That's just from basic econometrics. That's a regression coefficient. All right, so in other words, each asset has a risk premium, which is given by its beta with an efficient portfolio times the risk premium on that efficient portfolio, where by risk premium we just mean the average excess return over the risk-free asset. This is a property which is going to turn out to be very important. It characterizes all efficient portfolios C, including the tangency portfolio P, which we are talking about in class. Now, you know, this result is remarkable, and it's not obvious. We start with some arbitrary set of means, variances, and covariances. We take an efficient portfolio. What does efficient mean? It means that it has the highest Sharpe ratio. And then it turns out that that portfolio with the highest Sharpe ratio also has a very particular covariance with every single other asset. And the mean return on any asset is explained by its covariance with this tangency portfolio, or efficient complete portfolio. And this is going to be true ex post about sample mean returns and sample variances and covariances. And it's also true ex ante about the expected returns and the expected variances and covariances that investors have in mind. It describes any set of means, variances, and covariances. So in the remainder of this online module, what I'm going to do is prove this theorem. And the key idea we're going to use is that given an efficient portfolio, there should be no way to tweak the portfolio weights to make small adjustments in the portfolio weights that would reduce variance while keeping the mean unchanged. Because if you could do that, the original portfolio could not be efficient. All right, so now we're going to go into the details of proving this theorem. We're going to start with an efficient portfolio C, which has return RC. There's a weight on the riskless asset and a bunch of N weights on all the risky assets. And the sum of the weights, WF, and all the WIs has to equal 1. You have to put your money somewhere. Now we're going to consider making a local deviation from these weights. We're going to consider making a small increase in the portfolio weight of one risky asset, WI, and finance that by a decrease in the weight of the risk-free asset, WF. Now what will that do to the mean? It'll change the mean as follows. The derivative of the mean return on the portfolio with respect to WI is just going to be R bar I minus RF. And that makes sense because you're increasing the weight on this asset with this average return. You're reducing the weight on this asset which has this average return. All right, so that's the effect on the mean. What's the effect on the variance? Well, it turns out, and this is very important, that the change in variance generated by a small change in portfolio weight is twice the covariance of asset return I with the complete portfolio return. This actually is a very deep and important result in finance because it says that the way that an individual asset affects the variance at the portfolio level here on the left is related not to the variance of the asset return but to its covariance with the complete portfolio. So in a sense, the way we should judge the risks of individual assets is by thinking about their covariances. And that's a really key way of thinking that I want you to learn as you take this course in finance. All right, so what I'm going to do next is show you this result, show you that equation 3 is correct, and then we'll see what we can do with it. All right, so how do we derive that marginal change in variance that I showed you in equation 3? Well, let's start by recalling how the variance of a portfolio is calculated. What it is that this portfolio variance is the sum of all the terms in this matrix. There's the squared portfolio weight in asset 1 times the variance of asset 1. And then there's a term that looks like this. For an arbitrary asset I, we've got Wi times W1 times the covariance of I and 1. And we go all the way across to the right, and finally we have the last asset Wn W1 times the covariance of Rn and R1. All right, and then we work our way down through the matrix. The first column is going to be these covariances with W1, and the nth column is going to be the covariances with Rn, and so on. And of course the diagonal elements of the matrix are the squared portfolio weights times the variances. All right, so these are all the terms. We add all these up, and that gives us the overall variance of the portfolio. Now notice here that we're ignoring the risk-free asset because it has a 0 variance and 0 covariances with anything. All right, now what are the terms in that big matrix that involve Wi? Well, there's 2 times W1 Wi times the covariance of Ri and R1. Why does that show up twice? Well, if we go back, it shows up here in the first row and it shows up here in the first column, so we count it twice. All right, and then we have a Wi squared times the variance of Ri. And we keep going, we end up with 2 times Wn times Wi times the covariance of Ri and Rn. All right, so in other words, we get a Wi squared times the own variance, and then for all the other asset returns, we get 2 times W1 or whatever it is times Wi times this covariance. So now let's think about taking the derivative of this thing with respect to Wi. These are the only terms that change when Wi changes. So we'll take the derivative. What are we going to get? The derivative of the first term is 2W1 times covariance of Ri and R1. The derivative of this term is 2 times Wi times the variance of Ri. And we keep going. The derivative of the last term is 2Wn covariance of Ri and Rn. Now if we evaluate this sum of terms here, we're just going to get twice the covariance of Ri and Rc. Well, why is that? That's because the sum of all these covariances is the covariance of the sum. And what's the sum in here? Well, we've got W1R1, W2R2, WIRI, and so on, all the way up to WNRN. That's just the overall return, RC. Okay? So that shows you that the marginal effect of a change in portfolio weight on the portfolio variance is twice the covariance of Ri and Rc. Okay, so what should we do with that result? Let's go on. I'm now going to go back to proving the theorem, and I'm going to define this ratio of the marginal effect on the mean to the marginal effect on the variance. I'm going to call that the marginal efficiency ratio. It's just this effect on the mean divided by the effect on the variance. And from the previous results, that's the average excess return divided by twice the covariance. Now I'm going to assert that if portfolio C is efficient, this ratio should be the same for all risky assets I. And the intuition for that is that if this were not true, you could find a way to adjust the portfolio weights on 2 different risky assets that would reduce portfolio variance for given mean. But of course that can't be possible if portfolio C is efficient. All right, so the property of efficiency requires that this ratio here in equation 4 must be the same for all possible assets. Let's now look at that a little bit more carefully. Let's try to reach a contradiction. So let's suppose that the ratio in equation 4 is higher for one asset, asset I, than for another asset, asset J. So in other words, suppose we had an inequality here where this ratio is bigger than this one. Well, then what we could do is make 2 local deviations at the same time. We could adjust 2 different portfolio weights I and J. And the effects on the mean and the variance would be just given by the derivatives times the changes in weights. All right, so the effect on the mean would look like this with these linear effects. And the effect on the variance would look like this with, again, linear effects proportional to covariances. Now, what we could do is we could set dwj in relation to dwi so that the mean portfolio return is unchanged. All right, in other words, so that dr bar c equals 0. And in order to do that, we would need this to be the case. All right, dwj would have to equal this ratio here. Why is that? Because we're requiring that, back on the previous slide, the change in the complete portfolio average return is 0. All right, well then we can say with that change in the weight dwj, what happens to the variance of the complete portfolio return? Well, its change is given by this. We have dwi multiplying everything, and then there's the direct effect of dwi, which is twice the covariance of ri and rc. And then there's the indirect effect, which comes through dwj, which has this ratio to dwi, and that indirect effect is proportional to twice the covariance of rj and rc. All right, now we would find in this case that I'm talking about, we would find that this change in variance is less than 0. Okay? Why? Because we've got this inequality in equation 5 would imply, when we plug it in here, that the change in variance is negative. Well, that then would be a deviation that generates the same mean but a lower variance, and that would contradict the efficiency of the portfolio that we started with. So the inequality that I gave you in equation 5 cannot be correct. Instead, the ratio in equation 4 must be the same for all risky assets. Okay, now the final step to prove the beta representation theorem is that equation 4 must also hold if we make a particular choice of asset J, which is that asset J equals the complete portfolio C. Why? Because the complete portfolio C is an example of a risky asset, so the same logic holds. Well, now equation 4 will look like this. The left-hand side is the same as before, this ratio of mean excess return to twice covariance. The right-hand side is the ratio of mean excess return to twice the covariance of RC with itself, which is just the variance of RC. And if we now rearrange this equation by multiplying through by twice covariance, we're going to get the beta representation theorem, which is what we're aiming to get, that says that the average excess return on asset I is the ratio of covariance to variance, or the beta, times the average excess return on the complete portfolio. So that completes the proof, and that completes this part of the Lecture 7 module. Thank you.